By the end of this video, we will know how the F-distribution relates to the chi-squared and normal distributions. Understanding this relationship provides an intuition for when one should apply an F-test. Let's get started. Two independent random samples of sizes 10 and 12 are taken from two separate normal distributions with unknown variances sigma sub 1 squared and sigma sub 2 squared, respectively. S sub 1 squared and S sub 2 squared are unbiased sample variances. S sub 1 squared is equal to 4. You want to perform the following hypothesis test. The null, 2 times sigma sub 1 squared is equal to sigma sub 2 squared. Alternative, 2 times sigma sub 1 squared is less than sigma sub 2 squared. The p-value of this test is 1%. Calculate sigma sub 2 squared. Now, as you might have already noticed, this is going to be a very long video, and that's because I really wanted to walk through why when you divide two sample variances you get an F-distribution and can therefore do an F-test. So eventually when we get to the end, the calculations themselves are actually going to be really quick, and you could probably do this problem in 30 seconds if you knew exactly how to approach it. But starting off, let's just walk through what the F-distribution is. So first off, we have a normal 0, 1. And here I have color-coded the area to the right of 1 and to the left of negative 1. What we could do is say, well, what if we squared a normal 0, 1? So 0 would stay at 0. If you got a negative 1, it would move to 1. 1 stays at 1. Negative 2 would go to 4. 2 would go to 4, so on and so forth. So essentially what you're doing is folding the distribution in half and then kind of stretching it, and you end up with this resulting curve. And red plus blue is purple, so those perfectly overlap and we end up with that area. So we know that according to the Z table, that's 15.865 area to the right and to the left, and then we're just adding those together equals to the right of a value of 1 in this normal 0, 1 squared distribution. However, if you went to the chi-squared distribution table and went to degrees of freedom of 1, you would see that for a value to the right of 1, that area corresponds to 31.73. And that's because this is just exactly what chi-squared distribution is. It's taking the sum of squares of samples from a normal 0, 1. And the degrees of freedom here corresponds to the number of samples. So we're taking random samples from a normal 0, 1. So in our case, if you only took one observation, then degrees of freedom equals 1, and then that's why we can get these graphs. You can also say, oh, I'm going to take 2 random samples from a normal 0, 1, square both of them, and then add them together. And then that would be 2 degrees of freedom. Now, I've been jumping between number of samples and degrees of freedom, and that's because they're the same in the case where we know mu. So in the case where we have to estimate mu with the sample mean, that's going to change things, but we'll get to that later on. Alright, so now we know chi-squared is just the sum of the squares of samples from a normal 0, 1. What is an F-distribution? An F-distribution is just defined as the division of two chi-squareds where they're scaled by their degrees of freedom. So what I mean by that is down here in this function, you'll see in the numerator we have the summation of sum of squares of normal 0, 1s, and so that's just a chi-squared distribution, and then we're dividing by A. So there were A samples dividing by A. Again, assuming we know the mean, the number of observations is the degrees of freedom here. And so we're scaling it such that it's going to have a mean of 1. Because the expected value of a chi-squared is that, so that way it should equal 1. And then likewise, we're doing the same thing for the chi-squared in the denominator. So again, sum of squares of normal 0, 1s and then scaled by degrees of freedom. And the notation is just an F-distribution, and then the first number is the degrees of freedom corresponding to the numerator. All right, so now we know the definitions, what is a chi-squared and what is an F-distribution. And really it all comes back down to some manipulation of a normalized 0, 1. Next, just wanted to call out that when you estimate variance, the unbiased estimator for variance is going to be x minus x bar squared divided by the sample size minus 1. And I'll put a link in the description of this video. It's a proof walkthrough done by JB Statistics. I just recently discovered his channel. He has some really good walkthroughs, so I highly recommend using his videos whenever he has resources for what you're looking into. But for the purpose of this walkthrough, we're just going to take this for granted that this is the unbiased variance estimator. So with that, we can then say, okay, well, alluding to or foreshadowing what we're going to be doing, what if we had two sample variances and we wanted to divide one by another? So here I'm just taking the unbiased estimator and writing it for each of them. Now, in order to be an F distribution, we know we need normal 0, 1s. There are no normal 0, 1s. How do we convert this into being normalized 0, 1? And the way we're going to do that is by multiplying by 1 in a fancy way. So here we're going to say, well, what if our null hypothesis is that each of these variances are equivalent, so sigma squared? Well, then what we can do is just multiply this equation up here by sigma squared divided by sigma squared, so we're not changing anything. Move them into these calculations in the summation. And then finally down here, all I did was, right now I have sigma squared outside of this square term in the exponent, and I decided to put it inside the parentheses, so it's only sigma, and then it's going to get squared out here. So with that, we now see something that should look familiar. We have x minus its mean, its sample mean, divided by its true variance. And so we know that that is just trying to normalize it to be 0, 1. Now, the only issue remaining is that we're using sample mean here, not the true mean. And so instead of dividing by n, we need to divide by n minus 1 to account for that bias. And that's because when you measure squared distance from the sample mean, it's always going to be smaller or equal to if you use the true mu, because it's going to be biased towards minimizing the squared error. So that's why you need this n minus 1 instead of n. But with all that, we're now seeing something that's of the form sum of squared normals. It just needs a slight adjustment to account for the bias in using the sample mean. And this is just highlighting that comment here when you use the sample mean versus mu. So in summary, I know that was a lot, but starting off, a chi-squared distribution is just the sum of normalized 0, 1 samples squared. An F distribution is distributed as two scaled chi-squared distributions, and they're scaled by their corresponding degrees of freedom. Third, when using a sample mean, 1 degree of freedom is lost. If you're using that sample mean, you're going to underestimate, and so you need to divide by that bias to get an expected value equal to the true value. And then this isn't something I talked about yet, but in terms of specifically for MAS1, the tables were provided. We end up getting test statistics and p-values for to the right of the curve. And so when you're doing these f-tests, you need to make sure that whichever value is larger according to your alternative hypothesis is in the numerator. So when picking which variance should be A and which one should be B, you base that off of the alternative hypothesis and put the larger one in the numerator. So I'm saying we're getting in the calculations, but this first section I'd say is still kind of more general understanding, although it is applicable to our specific problem here. So we're going to start off by doing what we did before. We're just taking our sample variance divided by our other sample variance and just kind of see what we get. So again, we get these calculations on the right, and it's not quite what we want because we want to see normalized 0, 1s being squared. So I chose to multiply by this constant here. So it's 1 over 1/2 times sigma sub 2 squared. And the reason I did that was really I kind of actually started from here and worked backwards. So I knew that the denominator is sigma sub 1, and I know that sigma sub 1 squared is going to be 1/2 of sigma sub 2 squared. And so I knew that the corresponding standard deviation in terms of sigma sub 2 squared, so we want sigma sub 2 divided by the square root of 2 in order to get the standard deviation that corresponds to the sub 1 class. So really I started with knowing that this number needs to be here and that sigma sub 2 by itself needs to be in the numerator, and then kind of working backwards and realizing this is what I'm multiplying by. So all of this portion ends up down here, and then only the sigma sub 2 squared ends up here. And that leaves us with this 1/2. So we have 1 over 1/2, which is just 2. So we're left with this 2. So to summarize, we have sigma sub 2 squared divided by sigma sub 1 squared is equivalent to 2 times this thing. And we recognize this now that it's set up with the corresponding standard deviations as just being an F distribution with A and B degrees of freedom. Now, in order to do an F test, we just want this F distribution distributed variable to be by itself. And so what we can do is instead multiply all of this by the constant of 1/2, and that gets rid of this 2. So 1/2 times the division of our sample variances will be distributed as a F distribution with A and B degrees of freedom. So this was a lot more steps than you would ever need to do during the exam. So I wanted to walk through that so we understand where this 1/2 is coming from. But in terms of what you need to memorize to apply in a testing situation, you just need to know that when you divide sample variances by one another, they're going to be F distributed. You just need to multiply by the constant such that under the null hypothesis, it works out to be 1. So assuming that this variance is 1/2 of this variance, we know we need to multiply by 1/2 in order for everything to work out to be centered at 1. So that's kind of the shortcut that you can memorize for the exam, but everything up to this point was just meant to walk through where does this 1/2 come from, why is it there? Alright, so I would say now we can officially start actually walking through the problem. So the first thing is to, again, recall that according to the alternative, whichever variance is larger, that's what we want to put in the numerator. So our alternative hypothesis is that sub 2 is greater than 2 times sub 1. So that's why that's in the numerator. The second thing we need to know is that for degrees of freedom, it's going to be sample size minus 1. They don't explicitly say whether the sample mean was used or the true mean, but when they don't specify, I assume sample mean because that's typically the case. And so since we're assuming that's the case, we're going to use n minus 1 for each of the degrees of freedom. So we had 12 and 10 observations, so we have 11 and 9 degrees of freedom. We also know that the p-value for this test was 1%. So now we have everything we need in order to find our test statistic. So we know the number of degrees of freedom in the numerator is 11, right here. I apologize for the small font, and this is as far as I can zoom in. So you'll just have to take my word for it or look up your own F distribution table. So we have 11 degrees of freedom here for the numerator, and then we go down, we have 9 degrees of freedom for the denominator, and then there's all these values here that we could pick, and these are based off of what is your p-value or alpha level. So here we want to select 0.01 because we're told we know our test statistic resulted in a perfect 1% p-value, and so all of those line up to this cell, and that cell is going to be 5.178. All right, so we write down 5.178, so we have that here, And then we know that that's what our test statistic equals. So then we say, okay, well, what is the test statistic itself? Well, I know it's the division of the variances, sample variances, multiplied by whatever constant I need to make it equal 1, or an expected value of 1. Is just kind of a mental shortcut. So here we have this, and we were also given in the problem that the sample variance sub 1 is equal to 4. At this point, we got some elementary math, and we end up getting our answer of 41.424. Going up to the problem, we see that that falls in the range of E. So E is our final answer. The one final comment I wanted to make, it's kind of a last minute tidbit here. So something I want to call out is that null hypothesis for the variances to be proportional. So notice that in the initial walkthrough of background knowledge, we assumed the null hypothesis was saying they were equal. In the problem itself, it assumed that one variance was 2 times the other. And really that 2 can be any number so long as they're proportional. And then you can still work out this test. Thanks for joining me in today's lesson. If you found this helpful, please consider subscribing. Thanks.